Hey everyone, welcome to today's Explainer. We're going to be diving into something that sits at the absolute core of modern systems engineering, and that is data. Specifically, we're looking at how on Earth we store and query the absolute avalanche of telemetry data our systems are generating today. And we're going to explore this through the lens of ClickHouse. ClickHouse has rapidly become the de facto standard open-source sorting facility for managing these massive observability workloads. It's really fascinating stuff, so let's dive right in.
So here is the million-dollar question we have to answer. How do you query trillions of rows of telemetry data without breaking a sweat? I mean, how do you handle incredibly wide, high cardinality telemetry data without pre-aggregating it first? High cardinality data, so we're talking things like unique user IDs, span IDs, commit hashes. That is the absolute most descriptive and vital data for observability. But if you aggregate it before writing it to disk, you can literally never get that granular detail back. It's gone. You need a way to store raw events and then aggregate them at read time, instantly, across trillions of rows. Let's see how ClickHouse actually tackles this whole shebang.
Okay, here's a quick look at our agenda for today. First, we'll cover ClickHouse and MergeTree fundamentals. Then, modeling and collecting data. Third, querying telemetry with SQL. Fourth, vertical scaling and optimization. Fifth, scaling horizontally and globally. And finally, visualizing the data.
All right, Section 1, ClickHouse and MergeTree fundamentals. Looking right at the core of ClickHouse, we find the MergeTree engine. This is the foundation of nearly all persistent storage here. When data comes in, MergeTree organizes it into what are called parts, and these parts are totally immutable. It's a write once, append only model, which, if you think about it, is absolutely perfect for observability data. You just write the events, and then background processes continuously merge the smaller parts into larger ones, actually up to 150 gigabytes by default. Now, within these parts, the data is divided into granules. You can think of granules as contiguous blocks of rows. They serve as the smallest unit ClickHouse will actually index, so they act like incredibly efficient building blocks for your data.
But the absolutely crucial point here is how this structure translates to those blazing fast read speeds. When you run a query, let's say you're searching for a specific service in the last 10 minutes. ClickHouse doesn't just scan everything. No way. First, it uses primary key pruning via a binary search to drop irrelevant data parts instantly. Boom, gone. Second, it scans the index to identify candidate granules that might actually contain your data. And then finally, it performs columnar scanning only on those specific candidate granules to filter out the exact matching rows. It brilliantly skips irrelevant data, saving just massive amounts of compute. It's kind of like finding a specific book in a massive library, not by checking every single shelf, but by instantly teleporting to the exact row and section you need.
Moving on to Section 2, modeling and collecting data.
So there's always this constant tug-of-war in data modeling, right? On one hand, you have rigid structured columns. Now these give you incredible performance and compression ratios, sometimes like 20:1, for critical top-level fields like a timestamp or a service name. But as we know, modern applications evolve super fast. You're constantly adding new feature flags or pod names. Making a rigid, strict column for every single one of those creates massive friction. And that's exactly where the flexible map data type comes in. This allows for super agile handling of evolving, arbitrary attributes without the schema friction. So, what's the best practice? Well, it's a balanced approach. You want to keep your critical, frequently queried fields as top-level rigid columns, and then dump the rapidly evolving variable attributes straight into a map data type. Best of both worlds, really.
So how does all this data actually arrive in the system? Well, the open source standard right now is the Open Telemetry, or OTel collector, paired with the ClickHouse exporter. Out of the box, this setup adheres strictly to the OTel logs model. But what's truly staggering here is the sheer scale of this operation. A well-provisioned ClickHouse server can natively ingest tens of millions of inserts per second. Tens of millions. Just put that into perspective for a second. It does this natively without heavy coordination overhead. And if you happen to have strict durability requirements for your pipeline, it seamlessly supports sitting right behind alternative durable pipelines like Kafka or S3. So it's flexible, it's open, and it is incredibly robust.
Let's jump into Section 3, querying telemetry with SQL.
Now, a single, simple SQL query in ClickHouse instantly reveals request volumes across our API paths. But more importantly, it calculates tail latencies right on the fly, specifically the 95th and 99th percentiles. Because let's be honest, averages lie, right? Site reliability engineers absolutely need those tail latencies to spot real performance issues. By calculating this instantly from raw events, engineers can immediately prioritize the worst performing endpoints. For example, you might see an orders API taking nearly 1.8 seconds at the 99th percentile.
So you aren't just guessing based on aggregated averages, you are looking at the exact long-tail behavior of your system in real time. And here is a truly powerful capability for observation, the ASOF join. Real systems produce multiple streams of asynchronous events, right? You might have one stream for container failures and a totally separate stream for container recoveries. Notice how the ASOF join basically works magic here. It connects a failure event to the very next recovery event that follows it in time, dynamically calculating the exact downtime on the fly. You've essentially built a custom metric right when you needed it, linking disjointed event streams into a perfectly coherent timeline. It's a real game changer for incident response.
Next up, Section 4, Vertical Scaling and Optimization. Okay, before you go buying more servers, here is your rapid-fire vertical optimization playbook. We really want to squeeze every drop of performance out of a single node first. Number 1, profile your queries using ClickHouse's internal system tables. Don't guess where the bottleneck is, actually measure it. Number 2, use column materialization. If you notice a specific key inside your map data type is being queried constantly, materialize it. Pull it out into a dedicated column so it gets all the benefits of sorting and compression. Number 3, implement projections. If you normally query by service name, but sometimes you need to query by timestamp first, a projection creates an alternative primary key index under the hood, instantly speeding up those alternate queries. And finally, number 4, avoid redundant processing by heavily leveraging ClickHouse's multi-layer caching. Doing these things first will save you from the massive headache and cost of premature hardware scaling.
Now, part of vertical scaling is also managing your local disk space. This timeline shows a real-world data lifecycle management policy. Observability data usually follows very predictable access patterns. Recent data is hot, historical data is cold. ClickHouse handles this beautifully via automated time-to-live or TTL rules. Active, zero-day data sits on blazingly fast hot NVMe SSDs. But after, say, 90 days, a TTR rule automatically shifts it to cheaper object storage like S3. And after 365 days, it's permanently deleted. The beauty is, the query interface remains exactly the same to the user, but you drastically optimize your infrastructure costs by leveraging these different storage tiers automatically in the background.
All right, moving to Section 5, Scaling Horizontally and Globally.
Eventually, a single node will hit its limit. When you do need to scale out, you typically use a dual approach. For high availability and survival against hardware failures, you replicate your data using replicated MergeTree and the ClickHouse Keeper, which is a lightweight coordination service. But for pure horizontal capacity growth, you use sharding. ClickHouse uses a shared nothing architecture. This means the hosts for your shards remain completely independent, so they don't slow each other down trying to coordinate. And what if you're running a massive global operation? Well, you use distributed tables to unite those multi-region deployments, giving you global routing and geo-distributed fault isolation, all while maintaining a single unified view for your engineers.
Now, the evolution to true cloud-native elasticity introduces something called shared MergeTree. This is a cloud-native replacement for replicated MergeTree that is highly optimized for shared object storage. It completely separates storage and compute without the need for data sharding. Instead of nodes replicating data locally, all the data sits on shared object storage. The compute nodes just coordinate to stay in sync. This means you can scale your compute up and down almost instantly without the heavy lifting of moving massive amounts of data around the network. It offers incredibly high insert throughput and radically lower storage costs.
In our final section, Section 6, Visualizing the Data.
While you can absolutely just use standard SQL to query all this, most teams want an intuitive interface right out of the box. Enter tools like HyperDX. This is an open-source visualization layer built specifically for searching logs and traces natively inside ClickHouse. It offers intuitive timelines, real-time dashboards, and perhaps most importantly, a simple Lucene-style search syntax. This makes the raw underlying analytical power of ClickHouse instantly accessible to any developer on your team. They don't need to be a database expert writing complex SQL to go in and find the exact logs or traces they need to solve a production issue.
And that brings us to our final thought for today's explainer. We've seen how ClickHouse can ingest tens of millions of rows a second and query trillions of rows in milliseconds. It handles high cardinality data without breaking a sweat, scales from a single node to global clusters, and integrates seamlessly with open standards. So I want to leave you with this provocative question. In a world where open-source tools exist that are capable of parsing trillions of rows in milliseconds, is it time to reconsider proprietary SaaS models? Is it finally time to take ownership of your observability backend instead of simply renting it? Definitely something to think about. Thanks so much for joining me today, and I'll catch you on the next one.